Welcome back as we continue learning about equilibrium. So what are we going to be doing now? Now we're going to continue working with equilibrium constant expressions, but we're going to manipulate those values so we can use the equilibrium constant from one reaction to a similar reaction. So let me explain myself. So let's say that we have this reaction with a Kp of 226 times 10 to the 4 at 298 degrees Kelvin. And what we want to do is find the Kp, given this Kp, for three related equations. And there's some rules that we have to follow. So this is our parent reaction, and we know the Kp. So how does that reaction compare to reaction number one? And when you take a look at it, what you notice is that is backwards. So how do we relate the Kp or Kc to this situation? Well, we're going to take the Kp and we're going to find the reciprocal. And that's going to give us our new Kp. And if you think about it, remember Kp is the pressures of the products over the pressure of the reactants at whatever power they need to be. If we do 1 over Kp, what we're doing is flipping it, so the pressure of the reactants over the pressure of the products, which is what we did. We flipped the reaction. So if you flip the reaction, all you have to do is find the reciprocal, and that will give you the new K value, which is the same, in case that you see this form, which is the same as Kp to the minus 1. So that is exactly the same expression. What about number 2? Number 2, carbon monoxide, carbon monoxide. Number 2 is exactly the same, but we are dividing by 2. Divide by 2, divide by 2, divide by 2. So on a case like that, what we do is we take the Kp and we elevate it to the factor that we're using, which is 1/2 or divided by 2. To the power. We do it with the power. We're not divided by 2, but the power is going to be the factor that you're using to change that. And then when we take a look at number 3, and number 3, once more, we are flipping the reaction, but we are also multiplying by 2. So this is going to be then, we are flipping the reaction, but we are multiplying by 2, so we elevate it to that power. So those are 75% of the rules that we need to use. So let's review this. Given a value of Kp and our parent reaction, if you flip the reaction, you do the reciprocal of the value of Kp. If you multiply it by 2 or by 1/2, which is the same as divided by 2, if you multiply it, then you elevate the Kp to that factor. So the power becomes the factor that you're multiplying by. 1/2 on number 2 and 2 on number 3. Let's see the daily work. So based on what you just learned, you should be able to do this daily work. And the same with the next one. So we have one more rule to complete the set that we can use. Consider these reactions. So we have reaction 1 and reaction 2. And we're going to use these reactions under equilibrium constants to predict the equilibrium constant for this new reaction. So we are what we're basically doing on this case, we are combining those two reactions, we're manipulating and combining so that we can come up with that. We did something similar on 1411 when we were doing the Hess law to calculate the enthalpy of the reaction by combining several reactions. So let's see what we have here. First thing, nitrogen gas is one of the reactants. We find nitrogen gas on this reaction, but it's one of the products, so we know we're going to have to flip this one so that we have the nitrogen gas on the left side as a reactant. So let's flip that. When we flip it, we're going to have 1/2 N2 gas. Actually, that's what I put that note in there. Let's do it on the next page so we have more space. Sorry for that. So what are we going to do? We're going to take this one and we're going to flip that one so that the nitrogen gas is on the right side. So 1/2 nitrogen gas plus 1/2 oxygen gas produces nitrogen monoxide gaseous. In addition to that, we have on our target, the reaction we're trying to make, the nitrogen, we have a complete mole. So that means we're going to take all this and we're going to multiply it by 2, which is going to give us N2 gas plus O2 gas producing 2NO gas. What about the Kp? The Kp, which is 2.110 to the 30th, we're going to take that value and we're going to, first we flip it. So we're going to find the reciprocal. And then we multiply by 2, so we raise it to the second power. What about the other reaction? The other reaction, it have NOBr as a product. That's exactly what we wanted. But we need 2 of them. So we're going to take that reaction, NO gas plus 1/2 Br2 producing NOBr. We do not have to flip it because we have it exactly in the same way we want it. However, we have 1 mole there, so we're going to have to multiply everything by 2 to get what we want. So our Kp, which is 5.32, is going to be, since we multiply by 2, then we elevate by that factor. So let's rewrite everything then. So we have this reaction is what we're going to use. We already did everything we needed to do to that one. And this one, we're multiplying by 2. So this becomes a 2. This becomes a 1. And this, let me get some space here. And this becomes a 2. So these are the 2 reactions that I'm going to combine. So what do I get? NO and NO cancel. They are on opposite sides. So I'm going to get N2 gas plus O2 gas plus Br2 gas. So I use that one, and that one produces 2NOBr gas. Is that what we're looking for? N2 gas, N2 gas. O2, O2. Br2, Br2, 2NOBr, 2NOBr. What about the Kp? Well, since we added two reactions, every time we add two reactions, what we do, we take the respective Kp's and we multiply them. So our Kp is going to be 1 over 2, 1, 10 to the 30th to the squares times 5.32 to the square. So when you add reactions, their values are going to be multiplied. So quick review. Given a Kp, you can transform it into other reactions. If the reaction is just reverse, you do the reciprocal of the Kp. If the reaction gets multiplied by any number, you elevate it to that number. If the reaction gets added to another reaction, you multiply the respective Kp's. In this case, we did reciprocal, we multiply, and then we multiply the Kp values. So your turn. So go ahead and do this reaction giving these two reactions. And you have their case, so manipulate their case, do whatever you need to do to them to get to this reaction. And with that, you have just been introduced, pending more practice on Alex and so on, to manipulate equilibrium constant to reflect changes in other chemical equations. One more learning objective. Write the equilibrium constant expression for a heterogeneous reaction. So far, all we have been doing is homogeneous, meaning they are all in the same phase. So what happens when you have a reaction which is heterogeneous, like this one where you have gas, but you also have liquid. So you're basically going to have a bubbling liquid, which is a heterogeneous mixture because you can see two components. So, and it's giving us the Kc, and it's asking us to find the error. And the error is when you're doing equilibrium expression, you only include aqueous phases or gaseous phases. You do not include solids. You do not include liquids. So this is a liquid, so that doesn't go there. So the actual Kc is Cl2 over phosphorus pentachloride. So once more, equilibrium expressions do not include solid or liquids. They only include aqueous solutions, molarity, right, concentrations, or pressures. And that's why we have Kc for concentrations, aqueous, or Kp for pressures. Kc for concentration, Kp for pressures. And all you have to do is just give me the two equilibrium constants based on those reactions. The expression. And with that said, that was an easy objective. So if you have a heterogeneous reaction, do not include the solids, do not include the liquids on the equilibrium expression. And with that said, we can close up a lot of the objectives we have so far. So now you know how to relate equilibrium to the rate of the reactions. We did that at the beginning. You definitely know now how to write equilibrium expressions for homogeneous and for heterogeneous also. There's a formula where you can relate Kc and Kp. Make sure that you know what the delta M means. Make sure that you know that the T has to be Kelvin. And you know that if the equilibrium constant is a lot bigger than 1, it favors the numerator on the expression, which is the product. If the K value is a lot less than 1, it favors the denominator, which is the reactance. And you just learn the rules to manipulate equilibrium expressions to use it for variances of the equation that you're dealing with. With that said, we come out to the end of this section. So when we come back, we will start doing a lot of calculations. Until the next time, see you later. Take care.